Thank you, Mark. Thank you for being here. So, as a matter of fact, yes, this is actually directly connected to this lecture by Mark and to many other aspects that have been, of course, discussed in the course. The talk is in English, and the slides are also in English. I found that the title is more appropriate for the place to be in French, and this is why it is in French. So, all right, so let me maybe set up the framework, and this is all about asymptotically flat spacetimes. Actually, this renaissance of asymptotically flat spacetimes that we have witnessed over the recent years actually, of course, is mainly and mostly due to the observation of gravitational waves, but it goes also along with some attempts to extend the well-known asymptotic asymptotically ADS conformal field theory, duality, holographic duality relationship, to extend this beyond the natural framework of anti-de Sitter spacetimes. So this is what goes under the name of flat holography, even though maybe this is even premature to call it this way. Last but not least, I should also mention that this has also given some momentum to revisit parts of the quantum field theory, and in particular in the presence of massless particles, and this combined with the asymptotic symmetries has led to get a better understanding or a different perspective at least. So let me maybe just in a few words set up the stage and see or somehow show how this Carroll structure that I will be discussing in detail emerges from the asymptotic flatness. So probably the best way and the simplest way is to remind how the, oh, sorry, this is not expected, to remind how the the Penrose diagrams of these two extreme situations are. So here is represented the typical Penrose diagram of an asymptotically anti-de Sitter spacetime, and the main, well, one of the main features is that there is the so-called conformal boundary here. It's a conformal structure which is time-like. It's a vertical surface. This is time-like. This is the typical sort of spacetimes that you are used to and on which we sometimes can study field theory or quantum field theory, mostly, of course, in flat spacetime, but it can be a curved spacetime. Now, if the cosmological constant lambda, and here the cosmological constant is negative and parametrized with the inverse radius of the anti-de Sitter. So if this goes to 0, which means that the radius of anti-de Sitter goes to infinity, the structure of the Penrose diagram changes qualitatively, because now this vertical time-like hypersurface, infinite hypersurface, is now traded for this corner made of two scry plus and scry minus, which are the null infinities. So the region, the locus where any massless particles enters comes in, and the region where it gets out. And these are connected through this point, which is here a point in this diagram, which is the special infinity. This has been also discussed in length in the course of Marc 2-3 weeks ago. Now, the feature of this scry plus and scry minus is that this is a null hypersurface. This is the reason why it is at 45 degrees. And this is a natural place to find Carrollian geometries. So this is how Carrollian words appear here. Now, in particular, as it was reminded by Marc in the introduction, there is a conformal isometry group, a very specific conformal isometry group in this configuration, which is the conformal Carrollian group in n-1 dimension, and this is actually usually identical to the BMS group in n dimensions, which is the one of the asymptotic symmetries. Now, if flat holography exists, well, it is one could expect that it should be defined on a Carrollian spacetime. So this sort of Carrollian spacetime, or that one, or combinations of these two, and be BMS invariant. Now, I will not discuss, of course, holography in this talk. I will mostly discuss, actually, the structure of Carrollian spacetimes and some of its applications. So the tools, I will first present the tools. Well, some tools, and to some extent, of course, these can be geometric and isometry, so describing the geometry and the isometries that can be also come together. The dynamics and the conserved charges, this is somehow the bulk of what I have to say. And then, as applications, I will mostly discuss the reconstruction of bulk from data on the conformal boundary. This conformal boundary is null boundary. The way to obtain charges and dual charges directly from the boundary, based on the dynamics, on the Carrollian dynamics. And maybe I will also say a few words, even though this would be too ambitious to discuss all of these items together, about the realization of hidden symmetries, which are present whenever there is an isometry, of hidden symmetries from the boundary perspective. All right, so let's move on. First of all, I mentioned Carrollian and BMS. So why Carrollian? Just to remind you that the Carroll group, the group that we will be discussing, or at least which is behind this construction, is the Carroll group. And the Carroll group is an Inonu-Wigner contraction of the Poincaré group when C goes to 0. This is the dual contraction of the Galilean contraction obtained when C goes to infinity. Now, when this happens, now you can imagine how this goes. You have a space-time diagram, you have the light cones, and then when C goes to 0, the light cones shrink. So if the light cone shrinks, this means that, causality is no longer in place because there is no possible exchange, there is no possible motion, and this is how actually Lévy-Leblond came with the idea to call this a Carroll, of course, out of this, of the novel of Lewis Carroll. Now, in the same time, the Riemannian geometry, which is the geometry that you have started from with finite C, becomes what is called the Carrollian geometry when C goes to 0, which is a geometry equipped with other geometric tools, or different geometric tools, slightly different geometric tools than those appearing in the Riemannian geometry. Now, regarding BMS, I mentioned that BMS is, is the conformal Carroll group. Actually, this is, again, forgetting about Carrollian geometries and boundaries, this was actually proven to be the asymptotic isometry group in asymptotically flat spacetimes under a certain number of conditions that we have been discussing in this course. And sometimes it is infinite dimensional. So in 3 and 4 dimensions, it's infinite dimensional. Then you can argue about higher dimensions. This is not the purpose of the talk either. Now this was the global picture. Now more precisely, what a Carrollian geometry is. Well, the basic ingredients, so I'm here working in d+1 dimensions. Later on, these d+1 dimensions will be the boundary dimension. But for the moment, there is no question of boundary. This is a manifold, and it has d+1 dimensions. The coordinates I'm using here are t and x. And it is equipped with a degenerate metric. So this is somehow the defining feature of a Carrollian geometry. There is a degenerate metric. Now, I have here used a specific representation of this degenerate metric, which is maybe not the most general, but it is convenient for what we want to say. And furthermore, I have also presented when C is non-zero, this is a generic, metric which is non-degenerate for a d+1 dimensional Riemannian spacetime. This is a representation that usually comes under the name of Papapetou-Randers. So this is a generic metric. When C goes to 0, when you take the limit C goes to 0, then you are left with this piece only, which from the d+1 dimensional perspective is degenerate. It is degenerate and it has a kernel, and the kernel is actually part of the definition of a Carrollian manifold. This kernel is a vector, and this vector comes under the name of field of observers. And with this representation here, this vector is proportional to partial t. So these are the two basic ingredients of what is called a weak Carrollian structure. Now, you can equip this with another piece of information, which is the clock form. Actually, the clock form is very natural. It's not something genuinely new. It is just the dual form, the form which is dual to the vector, dual from the perspective of the cotangent space. Right? There is no more duality by raising and lowering the indices because the metric is degenerate. But there is a duality from the point of view of the frame and coframe. And this is written here in the most general form. This part with the time corresponds to 1 over omega partial t, but you have in general the freedom to add this bi dxi, and this is the Ehlers connection. So this is a piece of information that comes on top of what I had before. Now, I want to insist on the fact that this is, in the way that things are presented here, the general covariance appears here as what we should call the Carrollian covariance. So this whole structure, as it is presented, is invariant under Carrollian diffeomorphisms. So these are diffeomorphisms where time can be mixed with time and space, whereas space can only be mixed with space. This is the dual picture of what happens in Newton-Cartan, where you have Galilean structure. In Newton-Cartan with Galilean structure, time cannot be mixed with space. Time prime is a function of time, whereas space can be mixed with time and space. This is the dual picture of it. Now, in this parameterization, I think the tool, which is very powerful actually, is that the time components define Carrollian scalars, and the space components define Carrollian vectors or tensors in general. So there is a natural splitting of time and space, which therefore makes time being scalar and space being tensor. So you can therefore, in this language, raise and lower spatial indices. So you have tensors in this decomposition with respect to this Carrollian diffeomorphism group. You can split all the tensors of the space, of the manifold that you can define on cotangent space, and all the products of these with objects that carry spatial indices, and you can raise and lower the spatial indices with a spatial metric, and scalars, which are actually corresponding to the time direction. Now, I want to insist that this is not the most general expression. You may have the most general situation will be of this sort. You may have legs on time for the degenerate metric, and this will give legs on space for the field of observers. In this case, you will be working with general diffeomorphisms, and in this case, you will better use the splitting of the tangent and cotangent space. This is not what I will do, but you can do it. All right. There is no objection in doing things in this slightly more general fashion. So, in summary, what is here, there is a Carrollian geometry, and this Carrollian geometry is equipped with a degenerate metric, a field of observers, and on top of it with this Ehlers connection. This is a weak Carrollian structure, and you can now, of course, contemplate adding an affine connection on this Carrollian structure, because this is what you usually do in geometry. Now, what I will choose, what we have been choosing, is an affine connection which is metric and field of observers compatible. In other words, the field of observer and the metric are parallelly transported along this connection. This is a good tool, and I will say in a few minutes why this is natural. So anyway, for the technical details, well, I will not go through, just a couple of things. I will be using this coframe. Well, this is exact, but the time direction or the scalar direction is not. So this provides actually two tensors, the one that is called the vorticity, and the other one that is the acceleration. This comes from this expression. And now I introduce a connection, and the connection is tuned in a way that it is compatible with the time and space splitting that I have desired from the beginning. Right? I had time and space. We said that we want to separate the tensors in this way, and it's better if this separation keeps on being valid when there is an action of a connection, of a covariant derivative on it. And this is why we have made this choice of covariant derivative in the way which is presented here. The details are not important. One thing that I should add here, maybe for those who this may be reminiscent of something. Well, I could have chosen this to be traded for this covariant derivative of the field of observer along itself, it could have been also, rather than 0, being proportional to this vector. Now, this is equally strong in the sense that it is compatible. It's parallelly transported along itself, so this is fine. The coefficient that appears there is the unaffinity coefficient that would appear if this Carrollian manifold were, for example, a black hole horizon. Right? So if this tells something, well, that's the connection with it. So, well, then for the rest, well, we impose that it is metric compatible, and this is how these parts are determined. And then we end up with a connection which is metric compatible, field of observers compatible, but it has a torsion. Right? The combination of these parts plus the exterior derivative of the frame makes it having a torsion, but that's fine. I mean, this is not a problem. Now, this is not a Levi-Civita connection, therefore, but in any case, there is no real meaning or interest to choose a specific Levi-Civita connection, because in this framework it is not unique, because the metric is degenerate. Now, OK, you can also go beyond, which I will not do in detail here. You can define curvature tensors. You can also introduce a Weil-Carroll connection to make, when you have Weil covariants, this is important for the conformal structure of the boundary, you can have the covariant derivatives that keep on this, that are covariant also under Weil rescalings. Now, just let me motivate and also at the same time explain a few things why we have chosen this connection. As I said, you have choices, and we have chosen that specific one. And maybe I can say why, or at least clarify why. The reason is that this appears naturally when you consider this Riemannian or relativistic relation. Suppose that you have an energy momentum tensor, it is conserved, and you consider the expansion when c goes to 0. Well, this is the connection that we have chosen appears naturally in that framework. This is, I'm not saying that our connection is the limit. It doesn't make any sense to consider the limit of the connection. You consider the expansion in powers of c, and then you try to figure out what is the interesting part. So this is actually, explicitly, this is a relativistic Levi-Civita connection, well, I mean, a spin connection here, associated with the metric, the Papapetou-Randers, when c is non-vanishing, right? This is the metric, this is the connection, and from this you can read off the various pieces that I have mentioned in the previous slide. Now, what happens also is that when you have an energy momentum tensor, you can prepare what will happen in the Carrollian limit by decomposing, first of all, you'd reduce with respect to the Carrollian group, which means that out of this tensor, the time components become scalars. The time-space components become vectors, and the symmetric components, well, they are symmetric tensor from the Carrollian perspective. Now, each of these pieces can be expanded in powers of c square, actually. This is a natural thing that appears. And each of the things, of the objects which appear in here, will become the Carrollian tensors that we'll be using in the limit when c goes to 0. And from this way of doing, you can now read off, when you write down this expression of the divergence will come in various powers of c square, and each of these powers of c square will bring a Carrollian dynamics. You may have several, because you may have, this may be a series, it may be finite, but you may have replicas of the various objects, and the typical sort of equations that you obtain are written in this way, where the Carrollian covariant derivatives that I have introduced previously appear. The scalar, vector, and tensor which appear there are actually the remnants of the energy momentum tensor that should be here considered as momenta from the Carrollian perspective. All right, so are there any questions so far about the structure? So I repeat, it's the way that we have been doing this analysis, this Carrollian analysis, is to choose the Carrollian diffeomorphisms, decompose or reduce with respect to these Carrollian diffeomorphisms, and each of the decomposed of the reduced pieces expand in powers of c square and take the various the various comments. Yes?
Maybe I have a question. The Ehlers connection is an extra structure, no?
Yes.
There is a choice there.
Yes, actually, very good. So the Ehlers connection, so which appears actually here, so this piece, is an extra piece of information. It is not necessary, but it is necessary the moment that you want to have covariance under Carrollian diffeos, you have to introduce it, right? Because you see that if I put it to 0, the moment that I perform a transformation of this sort, it will appear. It's a connection, so you cannot set it to 0. It's a choice to leave it free.
But will you demand at the end that your results do not depend on that choice? Or?
Well, yes. This is part of the scheme that in principle, in the end, I'm free to choose it and to set it to 0 if I want a particular gauge, of course. Absolutely. All right, so now let me maybe say a final word about these Carroll structures. And this is about the isometries. So again, isometries are generated by vectors, and these are the vectors which are here written in general form. And notice that these are, well, they are diffeomorphism, Carrollian diffeos, and this is why the space does not depend on time, whereas the time component depends on time. And when you act with any vector of this sort on the field of observers, well, this is an identity. You find something which is proportional to the field of observers. This is not something that you impose. But then when you move on, well, then you act on the metric. Well, in general, you find something. And if you want this to be an isometry, you demand that this vanishes. Or if you want to be a conformal isometry, you demand that this be proportional to the metric, as we do in ordinary Riemannian geometry. Now, these are not enough. But as I said, this is not a constraint. This is an identity. And usually what you demand is an equation of this sort. So basically, what does this equation mean? It simply means that the field of observer has a weight -1 or a weight 1, whereas the metric has a weight -2. So in a sense, this is somehow a remnant of what you would have had in a Riemannian case. But it is not absolutely necessary. This is a choice. You may introduce a factor here, a constant. This is called the dynamical exponent, because here we are not bound to have this direct connection between the weight of the field of observers and the weight of the metric. This is a standard choice, but in the literature there is a Z usually which is there and makes a different structure. Now, the general so there are even other options that I will not be discussing. I mentioned this because this is the one that gives the BMS group. Now, a general property, now if you are given a manifold, the Carrollian manifold, equipped with all the nice equipment, now you go further and you ask the question, what is the conformal isometry group of this manifold? Well, there is a general, well, you have to work it out, but there is a general property which is the following. If psi ij is equal to 0, remember psi ij was this quantity. I mean, it was appearing, it was defined here, right? This is basically the derivative with respect to time of the metric, which is in general time dependent, and you subtract the trace. The trace is part of this. This is what it is. It's the extrinsic curvature with traces extrinsic curvature. That's what it is. Now, if this vanishes, and this is not very restrictive, because in all cases where the Carrollian manifold is the boundary of the asymptotically flat spacetime, this is imposed by the Bulk-Einstein's equations. So if you demand that, this means, in other words, that the metric has a time dependence which is factorized, then you can prove that the conformal isometry group is a conformal group of this metric, semi-direct product with super translations. This is very general. Now, of course, if you are in 2 dimensions, this is always conformally flat, and what you find here is SO3,1. Now, let me give an example, right, to make things Well, simple. Consider the flat, well, in quotation mark, because I haven't defined really here, at least I haven't told you what the curvature is. There is a curvature, but consider Minkowski space-time in Cartesian coordinates, send C to 0, and that's a good enough manifold. So this is the degenerate metric. It has only spatial components. The Ehresmann connection, well, here is a constant. Bi is a constant. You can set it to 0, but it is not necessary, because it changes anyway when you make a transformation. So with this space, the group of isometry is the Carroll group, and the group of conformal isometries is the one that I mentioned previously. It's BMS D plus 2. Well, it's Carroll D plus 1, and then this can be seen as DMS D plus 2. As I said, we can discuss about some details in higher dimensions, right? So this is the typical thing that we have. Let me, now we have the geometry, and now let's discuss a bit what the dynamics is on this geometry. Now, I start with the relativistic, and then I'll move to the Carrollian. Now, the relativistic, well, this is, well, it means that I have a pseudo-Riemannian space-time in D plus 1 dimensions. And, well, there is a general covariant action. I define an energy momentum tensor, and then I go through the properties of this energy momentum tensor. So general covariance implies that this energy momentum tensor is conserved. If on top of that I have Weil invariance, which means that the energy momentum tensor is, first of all, it is Weil covariant, and then furthermore, it is traceless. And then the bonus is that if I have a conformal killing vector, I can build a conserved current through contraction, and this conserved current makes it possible to build conserved charges. Right? This is a very elementary things. Now, maybe as a reminder, I could work in polyad formalism, so taking thetas and having a metric which is orthonormal. And in this case, using the diffeos is not so useful because everything is scalar with respect to the diffeos. You use the local Lorentz transformations and not the local Lorentz transformation invariance. This implies that this tensor that you built this way is symmetric. So this is so far for relativistic, and now we can go again and repeat the same scheme through the Carrollian situation. Now, I suppose that S is a Carrollian covariant action, so it is covariant under the transformations, the Carrollian diffeos. And then I can define momenta by varying the action with respect to the various geometric quantities. So variation with respect to the spatial metric will give the stress tensor. Variation with respect to BI will give the energy flux, and I will also have an energy density. And now Carrollian covariance will, I mean, you have to work it out, but eventually you will find, rather than nabla t equals 0, you'll find these equations written in the case where you have also Weil covariance. I wrote it in this way, so the derivatives are Carrollian, Weil Carrollian derivatives. The details are not so important. I will stress the important things. First of all, you have two equations, simply that you have time equation, this is the energy equation, and space, and this is the momentum equation. Second thing, you have an extra momentum, which was not defined by variational principle, that you must add. When you go through the variation in the action, you realize that you have a freedom, and you cannot dismiss this freedom. In general, you have a pi, which is the missing momentum, which is the momentum density. Now, if I had worked in a different frame, I could have defined this pi through variations as well. In the choice that I have made here with this Papapetou-Randers metric, this comes somehow as a bonus, but the equations are complete. And as I mentioned previously, Weil covariance, which is assumed here, is that the trace of the energy stress tensor is equal to the energy density. Now, I want to make some comments. This is the general structure, and by the way, these equations that you see, these precise equations obtained through variational principle are also the ones that I have shown previously as obtained here by considering the C-square expansion. These are the same equations, and of course, everything is consistent. Simply that in this case, I have written in general without assuming Weil covariance. The ones that I wrote just a minute ago assume Weil covariance. Good, so let me make a few comments. And the first is rather important, is again in the spirit of considering the polyad formalism. So now I consider if I write down the metric in terms of some one forms, and I write this in the delta ij form, you may now, in this formalism, inquire about the Carroll, local Carroll boost invariance. Remember that in the case of relativistic, the tangent space has naturally the action of the Lorentz group. Here, the natural action is the Carroll group, the contraction C goes to 0 of the Lorentz group. Now, if you make the analysis according to following the same tools, local Carroll boost invariance will tell you that Pi is equal to 0. So the momentum that I have introduced previously, dual to the Ehresmann connection, should vanish if you want to have local boost invariance. Now, you may say, why do I want to keep it? Because I will keep it. Well, the reason is that if these theories come from a relativistic theory, you don't have any control on whether the Pi is vanishing or not. The Pi appears actually when you consider the expansion of the energy momentum tensor, of this component of the energy momentum tensor, and it may or may not vanish. This is part of the possibilities, and it's better to leave it open. Actually, there is, as a parenthesis, there is a good example of that with the scalar field, right? The scalar field, relativistic scalar field, you consider the limit or the various possibilities of a Carrollian scalar field. You have electric and magnetic. In the electric, the Pi is 0. There is always Carroll boost invariance. In the magnetic, you have to impose something on top to have the Carroll boost invariance. There is a further constraint, which makes Pi vanish, actually. Now, what happens now, we have a dynamics, and then suppose that you have a symmetry. You combine symmetry and dynamics, and you find the conservation, right? This is actually what I have explained previously, but for the Carrollian case. Now, I suppose that I have a conformal Carrollian killing, and I have a dynamics. I basically consider the contraction of the killing and the momenta. So this comes in this more complicated way. This is a scalar, which is a time direction, and this is the vector, which is a space direction. These are the momenta of the dynamics, the p and the pi's. The xi's are the components of the killing. You combine the two, you find the current, you compute the divergence of the current, and of course you find that this divergence is not always 0. And this betrays the potential breaking of the Carroll boost. It is 0 if the vector is special, so if this vanishes, or if Pi is 0. Out of this current, you can build conserved charges. These are the Carrollian conserved charges, and these are conserved if this divergence is 0, but they are not necessarily conserved. Now, the important thing is that, in general, with this construction, once you have a dynamics, you build an infinite tower of charges automatically, because you have an infinite number of Carrollian conformal killing vectors. And for each of these vectors, you have a charge, which is not necessarily conserved for the reasons that I have explained there. Now, you may say, what sorts of applications can I have with this? And what are the instances where there is a conservation versus the instances where there is no conservation? So there are two main applications of these Carrollian geometries. First application is the black hole horizons, because the black hole horizon is a null hypersurface, so it is naturally equipped with a degenerate metric, not a conformal structure. This is an ordinary structure, but Carrollian. And in this case, there is a dynamics on this surface, on this hypersurface, which is inherited from the ambient Einstein dynamics. This is the famous membrane paradigm, and it gives equations which are Carrollian equations. Well, they were said to be Galilean and Navier-Stokes. Actually, the equations are right, but the name is not good. Now, in this case, there is no energy flux in this dynamics, and therefore it is conserved and it's fine. Now, the other instance is for Ricci-flat spacetimes at Scri. This is a situation where you study the boundary, and in this case, there is an energy flux. and you can immediately guess why. There is an energy flux that will betray, that will be signaled by the absence of conservation. This is because of the outgoing or incoming gravitational radiation, and this betrays actually the fact that is one of the manifestations of this radiation is that this flux is not there is an energy flux, so you have less conservation for some charges.
But don't you have a flux also in the case of horizons?
Well, it seems that in this case it does not affect the pi I. Yeah. So I will now, this is the next part. These were the tools. Now I will show how these statements actually have make sense about this conservation or non-conservation and the fluxes.
So somehow it looks like the first case would correspond to electric Carroll and the second case to magnetic Carroll. There is some kind of duality.
Between these two?
Yes.
All right, so no, I don't think there is a well, not in the sense. I will discuss electromagnetic manifestations of this. Now, but maybe I can make a comment. Maybe you have in mind the behavior of the nut charge, whether it's conserved or not. Is this what you have in mind when you make this comment?
No, it's more elementary. The fact that in one case pi I is equal to 0.
Yes.
This was somehow related to the electric limit.
I see. Oh, I see. You are referring to the case. Okay, no. This is definitely not this. We will see that. Well, no. The answer is no, and maybe it will be clarified in a moment. Very good. Other questions or comments? Yes, please.
So how do you square the intuition that in C to 0 limit nothing moves with the fact that you still have non-trivial dynamics?
Yeah, I mean, it's you have a non-trivial dynamics, but you don't have velocity. Let me make it clear. If you do the C goes to infinity limit, for example, for fluids, right? You start with the relativistic fluid energy momentum tensor, nabla equals 0, etc. You have the limit. In this case, you have again a momentum and an energy flux. Those are expressed with the conserved current, the U1 conserved current, and there is a density and the velocity. So you have there, you see that there is a velocity. Here you don't have a velocity. I cannot re-express the momenta in terms of a velocity. I can re-express this momenta using, if you want to do a fluid perspective, in terms of what we call an inverse velocity. But this is not, it's kinematical, but it is not a velocity. The dynamics here somehow, even we mentioned the Carrollian scalar field, right? In the Carrollian scalar field, you can see in some situations, it's very simple, you can see that actually it's a dynamics which is at each point, right? It's not, and then you can also see the nature of the correlations that you can build. I mean, in concrete examples, you see that indeed there is a dynamics, but it is not a dynamics that connects, information flowing from one point at a time to another point at a different time. Things remain at the same points. Well, it's a weird. This is the reason probably why we have, I mean, at least personally, and we have never really tried to go beyond this sort of interpretation, rather than using this as a tool to investigate, like what I will do now, the boundary, the asymptotic null infinity. Yes.
I didn't really understand if Carroll groups are supposed to be part of the conformal Carroll group.
Well, wait a minute. This is a good point. The conformal Carroll group is the isometry group of a flat space. Now, if you are not in a flat space, if you have a very complicated manifold, you may not have any isometry, right? It's like in ordinary relativistic space. Minkowski space has an isometry group. Now, if you go to a curved space, you may have lost all of your isometries. However, in the tangent space, you still have an action of the Lorentz group in the Riemannian case, the Carroll group in the Carrollian case, right? So then you may ask whether this is this local this gauge invariance that you usually have by moving the frame is valid or not. Right? You can impose it or not. I know that this is sometimes surprising, but it is like considering, and let me maybe take 1 minute to do that, to make it clear that it is not something exotic. This is what I'm trying to say. You may consider in relativistic situations, you may consider, nabla T equals 0, where T mu nu has a symmetric part, an anti-symmetric part. Now, what you do, you can keep the symmetric part on the right-hand side, push the anti-symmetric part with the nabla on the right-hand side, and say that this is an external force, right? Which, of course, the moment you have external things, well, you may break some of the tangent or cotangent space symmetries. That's the way to see it. And in the specific case that I'm explaining here, this momentum, which is non-zero in the null boundary, is non-zero because precisely it receives information or contributions from the gravitational radiation. Okay, let's, well, time flows, and then maybe just, well, I have to talk about the cotton because this is an important part. So quickly, the cotton is a tensor. It is defined in any dimension, but in 3 dimensions, it can be dualized to give an object which has 2 indices, which is symmetric, and which is traceless, and it is conserved, identically conserved. This is following Bianchi identity. There is no dynamics. Take any 3-dimensional space, it has this property. It is furthermore Weil covariant, and actually, if it is non-vanishing, it betrays that there is the space, this 3-dimensional space, is not conformally flat. Now, I want to make clear that now, if you have a conformal killing, you can contract the conformal killing with the cotton and then build the current, which is a conserved current. And from this conserved current, you can build a conserved charge, which is always conserved, irrespective of the dynamics. Right? This is off-shell. Now, of course, you can also go and take the limit of the cotton. What do I mean? The limit means that you start with a good frame that I have presented. You have a scalar with respect to Carroll diffeomorphisms. You have a vector and you have a tensor, which is here even make traceless. You expand in C. Where here it's not an expansion. This is exact, right? These are all the pieces that you find. The expression is irrelevant for what I have to say. You find these pieces. And now the divergence of C equals 0 gives a list of conservation equations. For there are 4 sets of conservation equations, which are actually, this is the Carrollian dynamics, the Carrollian cotton dynamics, and generically the local Carroll boosts are broken. Now, you see that you can, in the same way, now construct charges. The Carroll cotton charges will be constructed using the procedure that I have explained previously, valid for the Carrollian. I said conserved, not necessarily. You have infinite towers. Each of these dynamics gives a tower, but they're not necessarily conserved because of the possible breaking of the boost. Now I want to apply this to the reconstruction of the bulk for them. You can say a few words about more general, but we have done it for 3 and 4. This is for 4 here. Now, you can do it as you do it for Einstein. So there are boundary data, which now are defined on the null boundary. These boundary data obey Carrollian dynamics. And from this, you can reconstruct the bulk Ricci-flat spacetimes. Two remarks. First of all, the number of data now are infinite compared to what we had in Einstein spaces. And as in Einstein spaces, they contain explicitly the cotton tensor, which has some meaning that I will describe. Now, let me say the spirit. Of course, I cannot give details. Let me say this, try to explain or describe the spirit of the construction. Now, suppose that I'm in n dimensions. Capital G is a metric in n dimensions, and I want to solve either with a cosmological constant or Ricci-flat. So I choose coordinates. I set up a gauge fixing, and then I suppose that the system is isolated. This is what Marc has done in the course actually this year and also previously. And then we try to find out what are the various species at each order, what sorts of equations it obeys. Of course, here I have not even mentioned the logarithmic terms, which are also present. All this is somehow under control. And the solution space is the collection of all these coefficients of the expansions of the various species that you have. Now, a desirable feature, and this has been our point of view in these works, is actually that we would like to these quantities to be, and their dynamics, of course, to be organized around a covariance principle, which makes the whole thing covariant. Now, what do I mean? If you, for example, consider the Pfefferman-Graham gauge, it is covariant in the sense that at every order in 1 over R, you have an object which is a tensor with respect to the boundary. And you reconstruct, the whole space-time using the first fundamental form, which is a boundary metric, the second fundamental form that you interpret as the energy momentum tensor, and the other things are described in terms of those. But it is covariant. Unfortunately, it has a singular k goes to 0 limit. You may choose a Bondi or Newman-Unti gauge. These are good gauges either for non-zero cosmological constant or for zero cosmological constant. However, these gauges are not covariant. They are not covariant with respect to the boundary properties. Let me be precise. Let me choose the Newman-Unti gauge. So the Newman-Unti gauge has these gauge conditions. This one is the one which replaces the determinant condition of Bondi. So the reason we are choosing this gauge rather than Bondi is the following. In Bondi gauge, the determinant condition is good because it tells us about the evolution of the spheres and the luminosity. The advantage of the Newman-Unti is that the congruence partial R is geodesic as it is also in Bondi, but in this case, it is affinely parametrized. This is an advantage if you want to propagate null tetrads because they are parallelly transported. Well, this is one this is one advantage, and this has been helpful to us. Now, this is therefore the expression for the metric in Newman-Unti gauge, and you can see immediately that this is not stable neither under Carrollian diffeomorphisms, which are the boundary diffeomorphisms that we would like to have, nor under Weil rescalings. So you need to enlarge, to extend this gauge. You need somehow to make a choice of an incomplete gauge fixing. Therefore, you have to trade the GRU from -1 to a general function and the GRI to a general function as well. And this is how the Ehlers connection comes into the game. The Ehlers connection of the boundary Carrollian manifold. Good. Now, I would like here, now the purpose of this slide is, I go back for 1 minute to Einstein case to come back to the role of the cotton tensor. I mentioned the cotton because I said that this was an important piece of information. Why? Now, again, I can go through covariant Newman-Unti gauge for anti-de Sitter space. There, as I said, as much as in Pfefferman-Graham, there is a metric on the boundary. There is an energy momentum tensor. And Einstein's equations for the bulk summarize in this conservation of the energy momentum tensor on the boundary. Now, it turns out that the boundary has also a cotton because it has a metric, it has a cotton. In general, the cotton is set to 0 in usual holography, but I'm not doing here holography, I'm doing reconstruction. So there is in general a cotton, and if the cotton is non-vanishing, which means that the boundary is not conformally flat, from the bulk perspective, this is translated to the property that the bulk is not globally asymptotically anti-de Sitter, but locally. If there is a net charge, there is a magnetic mass. Now, if now on the boundary I have a conformal killing, well, I can build 2 conserved charges. One with the cotton and the other one with the energy momentum tensor. The one built with the energy momentum tensor is conserved on shell because it requires this equation, which is an equation of motion, whereas the cotton part is conserved off shell. These are the Komar charges. This is the magnetic current, and this is the electric current. And you can build the charges associated with this conservation. Those will be the electric, and those will be the magnetic. So from this sort, you will have the mass. From this, you'll have the net charge. So the same scheme actually appears when we do things from the Carrollian perspective for asymptotically flat spacetimes. So this is the main message somehow, and you can now go on and see how things go. Now this is really the heart of the discussion about asymptotically flat, so Ricci-flat spacetimes. So now I make here a sort of rough summary of the ingredients that you need to reconstruct a bulk from the boundary. As I mentioned previously, what happens in ADS. In ADS, it's simpler. Here, it is more complicated. And I'm here using, of course, the language, the Carrollian language, which makes everything covariant from the Carrollian perspective. Maybe I should mention here already a remark that usually make towards the end, but it is good to make it now. To motivate also the reason why we are insisting, one of the reasons that you can possibly advocate for insisting in having these covariants. These covariants, remember, the Carrollian diffeos, are where we said x, the spatial part, is sent to x prime, which is only a function of x, and then time is sent to u prime, which is a function of u and x. And in all the scheme, everything is covariant with respect to this. Now, notice that super translations belong to this sort, which means that in this approach, all the ingredients that we are introducing are invariant under super translations. So this is something that, well, in view of the last lecture of Marc and the next talk by Massimo, might have some importance in trying to compare the gauge and try to see the interplay between the issues about the angular momentum that was raised last time and in this approach, whereas compared to the other approaches. So this is one way of, again, see that it is interesting to have something which is covariant with respect to these transformations. Now, let me summarize what you need. See, I have here sorted out things in powers of r, right? So at order r square, well, you need the geometry. And it's a Carrollian geometry, so the degenerate metric and the Ehlers connection, and this, well, with the constraint, and this comes from Einstein's equations that Xij equals to 0. Remember, this is the traces part of the extrinsic curvature of the spatial section of the boundary. Now, at 1 over r, this 1 over r is where you have usually, in anti de Sitter at least, the energy momentum tensor. So here you have what I could call the momenta, fluid momenta. It's not a fluid, but you could think in this way because you had originally a T mu nu. Here you have momenta. Now, those appear as an energy density, the famous capital pi that I had introduced previously, and this is actually the body mass aspect. And you have a momentum density and a stress tensor. These are the Ni and Eij. These are standard notations. However, be careful, those are defined in our gauge here, which may be different from the ones usually defined in the Bondi gauge. There may be shifts between these two, and we have to be careful about that. See, in the similar fashion, at order r, there is the shear. And again, this shear is not exactly the shear of the Bondi gauge. There is a shift, because it is defined in this gauge, which is a bit different. And then you have, at every other order in 1 over r and higher, you have other data which obey some equations, which are again Carrollian dynamical equations. And these Carroll dynamics in this language of the boundary scry are called the flux balance equations, because these are not exactly conservation equations. They are equations that have a source somehow, and this is due to the presence of radiation. So what I want to show now is a specific example in the next slide, maybe the next or the next to next, where you can see exactly these equations, how they look like, and understand the role in this gauge of the cotton as part of the radiation. Now, before doing that, I just mentioned here precisely, again, the Carroll cotton. Remember, the Carroll cotton was obtained by reducing and expanding the Riemannian cotton. But because of this condition, which is imposed here, we have less piece of information. There is one scalar, two vectors, and two traceless tensors. And those obey these simple dynamical. These are identities, but these are, again, at the same time, Carrollian dynamics for the cotton. Now, the interpretation of the pieces that appear in the cotton and that will also appear when we will express the bulk metric in terms of the boundary are as follows. The scalar of the cotton, the scalar appropriate normalized, is the nut aspect. This is the magnetic mass. Right? This is the magnetic mass, which is dual to the body mass aspect, and those can be combined to create a complex mass, which is both the magnetic and the electric. And these pieces enter in the bulk. They're explicitly in the bulk. Now, there is here the chi-I, which is there, is a Carroll cotton energy flux. So this is a typical thing that breaks, a typical object that breaks the, as I said, the Carroll boost, the local Carroll boost invariance, but it appears here naturally, and in this gauge, I don't have no reason to set it to 0, because it contributes precisely the losses through gravitational radiation. Of course, there are many other things that I don't want to discuss. These are technical things which, again, show the role of the cotton tensor in this Carrollian, perspective. Now, let me show you what happens in a specific case, how the metric of the bulk looks like, and what the flux balance equations are. So this is the simplest possible case, because here I have removed almost all degrees of freedom. I have kept only the energy density. This is actually the situation where it is resummable, so this infinite series can be resummed, and this corresponds to algebraically special cases. Now, you see, this is the expression of the metric, which is resummed. The only pieces of data are, as we said, the geometry. This is expressed here. The body mass aspect, the energy density, the Carrollian energy density, and that's it. It is resummed because there is a 1 over rho square, but this 1 over the rho square is r square plus a scalar, which is the dual of the Carrollian vorticity. And of course, this is an infinite series that has been resummed. And the Einstein equations and cotton conservation equations are the famous flux balance equations, which I have expressed here. There are 3 of them. These three equations, 1, 2, 3, and they capture, of course, the whole complex mass, time derivative, and in this here there is a time derivative of, well, what appears as the momentum. So these are the equations that you have to solve. These are the flux balance equations, and you see that this chi is exactly here playing the role. I could put it also on the right-hand side. It tells how the mass, complex mass, varies with time. This is a piece of the cotton which dictates the behavior in time, and this betrays, as I said, the gravitational radiation. Now, this is a very simple case, but it contains a simple, which is the Robinson-Trautmann. The Robinson-Trautmann is an exact solution up to solving some complicated equation, and this is the equation which is there. It is a radiating solution. And this gauge, the gauge that we have expressed here, is the natural gauge for this, the defining gauge almost for this Robinson-Trautmann, where the whole gravitational radiation in the balance equations are contained in this flux. So now for those who like the Newman-Penrose formalism, I have also made the translation. Because, as I said, this choice of gauge makes it possible to have a null tetrad which is parallel transported. This is a null tetrad. Well, I mean, the dr is a null tetrad. The rest is you have to define, but it can be defined. Since I have put the shear to 0, thanks to Goldberg-Sachs theorem, this is algebraically special. This is what I mentioned. And in this case, the first psi's are 0. Psi 0 and psi 1 are vanishing. The others are given in terms of the data. So psi 2 is given in terms of the complex mass. Remember, this is the combination of the cotton and the energy density. And then the cotton enters in the psi 3 and psi 4. The chi here is precisely the famous flux that we have, that I have stressed several times. This is a Carrollian tensor. Of course, in general, well, the psi 0, at least the first component of the psi 0 will be related to the stress. And for psi 1, it will be related to the angular momentum aspect. And these are the flux balance equations that I have borrowed from the paper of Newman-Penrose. These are exactly the three equations which are presented here. So the match is perfect, and the interpretation, this Carrollian interpretation, is something that gives another perspective to this Newman-Penrose approach. Now, let me also mention what happens in the general case. I will not give details, but it is also good to see the structure, right? So now if I keep everything, so I keep the whole 1 over r, I keep the r, which is the shear, plus all the others, 1 over r squared, etc. This is how the Ricci-flat metric looks like. I mean, it is rather familiar in the sense that you recognize things that are similar in other gauges. The difference is here that you can make any choice for the gauge of the boundary. It is fully covariant. And you can also define nus. Again, these nus are not exactly the ones that you find in Bondi. They're slightly different. The advantage of the formalism is that here the Cij was a traceless shear automatically. But since we are using Weil covariant derivatives, the nus here are also automatically traceless. You can define also correct the epsilon with the piece that gives the Bondi mass. And this is how you find finally the famous complete set of flux balance equations that I have advocated from the very beginning. The three first equations are the ones that we had already, but now there is a right-hand side which contains the shear and the nus, as usual. And you have further equations for the next pieces. And again, these equations match now the 4 equations that appear in the Newman-Penrose paper. So this is the scheme. And now comes the question. We have this scheme of Carrollian structure. We have, in a sense, found a nice, well, convenient and systematic way. How can we have an idea about the charges which are behind? So this is the final part of the lecture. How, from purely boundary perspective, I can find the Carrollian boundary perspective. I can find the charges and define them. Now, this is, I mean, I have almost said everything. The general strategy is very simple. If you have a dynamics and if you have a symmetry, you can marry these two things and find conservations and extract charges from this conservation. That's the perspective that can be applied on any space-time, and in particular on the Carrollian space-time, which is the boundary of 4-dimensional spaces. So what happens is that at every order, there is a Carrollian dynamics. This is one piece of information. Furthermore, we know that there is an infinite tower of Carrollian killing vectors. This is the other piece of information, which is also general. And in 4 dimensions, we know even very precisely what this is. Therefore, every Carrollian set of dynamics will produce an infinite tower. I'll give an example. This is a resummable case. Right? The resummable case is given here. So this is, remember, this was the expression of the metric that I have given, but now I want to expand it to somehow investigate what happens order by order. So I expand the 1 over rho square, and therefore I have powers of star pi, which is the vorticity. So at every order, at every order, I have one dynamics. At 1 over r, this is the epsilon, the energy density. At 1 over r square, I have the magnetic charge. And then I go 1 over r cube. There is the energy, but it's multiplied by star square. So, but again, even though it looks trivial, I have every time a different Carrollian dynamics that I will now marry with the Carrollian killing vectors, conformal killing vectors, and find charges, which may or may not be conserved. Now, what is important is that everything here, you have a whole net of towers. At every point, you have an infinite tower of charges. You can also see things differently. For every conformal killing vector, you have a tower of electric or magnetic charges that correspond to this vector. Now, let me give a very specific example. You can now do that, take this solution, take the killings, put things together, and find the charges. So this is what you find. In a specific case, even though it is simple because it is Kerr-Taub-Knut, and this is, of course, a stationary space-time, nevertheless, this is the way, this is to illustrate what you find when you do these things. So you consider the killing, conformal killing, which is here even the killing of the space-time. This is the partial U. And then from this, you find the multiple moments. You have infinite series of magnetic and an infinite series of electric multiple moments, the mass multiple moments, and this is the expression that you find explicitly. Now, you may choose another one. You may choose the partial phi, and then you'll have the angular momentum multiple moments. This is in light gray here because it is not important to have all the formulas visible. This is what you find in general, and in particular for s equals 0, this is what you find. These are the expressions of the moments that were found actually in 70 by Hansen and Geroch. And in general, and this is the last word actually about, I cannot, first of all, I cannot talk more, and then not everything has been completely settled, but this is the general scheme. This is what you find. You find actually that for general Ricci-flat, at every order, you have a Carrollian dynamics, and at every order, this Carrollian dynamics together with the conformal killings gives charges, not necessarily conserved. So you have the soft charges here. Even at the metric, you have charges, which are, you have what I have called here the curvature, electric and magnetic charges. These are conserved, always. These are geometric charges regarding the manifold, actually. Next order, you have the bond electric. After that, all these give charges, but which are not conserved. Next, at 1 over r squared, you have the bond magnetic. And you have the famous Newman-Penrose charges. You have many charges here. Not all of those are conserved, but some of those are, and these are the Newman-Penrose. And you can go on. Now, there is, of course, questions about the next steps, but I don't want to discuss this. All right, so this was all about the way that you find the charges. So to summarize, you have a landscape of charges which are not necessarily conserved. At each order, you have a dynamic. Some of these dynamics are magnetic, some are electric, and some of the charges are conserved, some are not. But this is, at this stage, performed using purely boundary considerations. So as a final word, let me just mention, I have not even prepared anything technical about this, the hidden versus visible symmetries. This is the last thing that I want to say, because I mentioned it in the very beginning, and this was also, actually, to tell the truth, the original motivation for making the analysis of the charges. So this is about spacetimes, Ricci-flat spacetimes, which have isometries. So if there is an isometry, I can make a reduction with respect to the isometry. So I can make a reduction by modding out the orbits of the isometry group. When you do this reduction, you find that in the reduced dynamics, there is a symmetry, which is called hidden because it is not visible from the four-dimensional original dynamics. So, for example, if I have a killing vector and make the reduction from 4 to 3, there is an SL2R group, which is called the Ehlers group, which appears. So this is something which has been known for a long time. If you go from 4 to 2, it's the Geroch group, and this is even affine, so this is even infinite dimensional. You can do the same thing in many situations. You can start from 11 dimensions, go to 2, and have exceptional groups appearing. Now, and these are actually non-local actions. The reason is that the typical example of action is an action that moves from an electric charge, so Schwarzschild, to Taubnat. So you rotate in the plane of electric magnetic charge. And this is not a local action. It's not a local diffeomorphism that can do that. And the question that we had in mind when we were analyzing this group is what happens on the boundary. Since now we have the tools to describe everything on the boundary from a boundary perspective, what is the action of this Ehlers group on the boundary? Well, in a summary and without any technical detail, it is realized as locally on the boundary. So basically here, I have here given a specific example, but this is rather generic. Remember, this was the complex mass, and the typical action of the group is to rotate this complex mass. Part of the group is diffeos, right? Not the whole Ehlers group, or not some of the actions are diffeos, but there is always a U1 which is inside, which is not diffeo, and this is the action which is local from the boundary perspective. Let me conclude. All right, Sam. So through this overview, I have several, well, simple messages somehow to go through. The first that I have insisted a lot was about the boundary Carroll covariant structure, right? We have somehow moved from situation where it is not covariant, like Bondi or Newman-Unti, to situations where it is covariant. This is at the expense of relaxing the gauge fixing. This is at the expense of relaxing the gauge fixing because we need precisely to recover this boundary Carrollian diffeomorphism, you need to relax even the bulk gauge. Now, the effect is that this may lead to extension of asymptotic symmetries. So this is an analysis that requires care. We have done that in 3 dimensions. This was not the subject of this talk. We have done that in 3 dimensions, and then you can see, you can go through all the steps and check the charges, check the algebra that you find, and that everything is consistent, that there is nothing somehow spurious that you add in the system when you do that. The second remark is that, of course, as I mentioned already there, but I think it is important, is that supertranslations leave all the Carrollian tension C variants. So I would, therefore, it would be interesting to somehow reconsider what is said about the angular momentum in this perspective, how this can be translated or understood, yet from a 6th way. You said last time that it was at least 5 ways to understand it. Well, maybe a 6th one is also good. So Ricci-flat space-time reconstruction from boundary data. So this is also, of course, this was the main, right? The main purpose, well, one of the main purposes was to do that. Then, of course, the Carrollian boundary dynamics and the non-conserved charges. Since we have all these dynamics and the symmetries, we can construct charges and analyze their conservation. Now, this is what we have done, but not completed, of course. We have also stressed the Carrollian cotton. Remember, the Carrollian cotton seems to play a role. It is present in the language of Newman-Penrose, but it was not identified as this specific object. And it turns out that it appears, as I said, in the psi's. It accounts for gravitational losses. Well, the shear plays a role, but also the cotton plays this role. And it also appears to distinguish the magnetic charges and the dualities that are related with them. So finally, well, I mentioned very quickly yet another manifestation of an electric magnetic duality, which is this SL2R of Ehlers. But there are several questions, of course, and challenges that I here go through quickly. Of course, I think that compare this simple approach of the boundary with the more general methods that have been used for the bulk computation of the charges and the towers of charges, and the recent analysis of several groups about what they have been calling the subleading charges, since they appear at every order in 1/r. I think this is yet it's yet to be done. We haven't made much progress about it. There is a question, of course, which I think has not yet, I mean, from discussions we had, not completely settled. Are there further conserved charges beyond 1 over r squared? Remember, 1 over r squared is where the Newman-Penrose are sitting, but you can go beyond. Are there others beyond? Do we have a good tool here to probe whether some other charges exist which would be conserved? What is the relationship between integrability and conservation? I have discussed conservation only. The idea of integrable part of the charges is this is somehow our method is transparent. We don't see this, and it would be nice to understand it as well. Well, there are other questions. The contact with the log BMS4 that was discussed last time. The contact with the mixed signature plus minus minus is also an interesting question. And finally, maybe also, you know, after all, applications of flat holography in comparison to the celestial approach might also be helpful. I have, from my understanding, if I take this little formula that I have already presented, celestial holography is sitting essentially on this part, right? And there are all the other parts well, it's a good question whether this could somehow shed some light or how the two approaches could be combined. Voila, thank you.